Hi, I'm Raina Fitzgerald, and in this lesson, we're going to look at the multiplication and division of rational expressions. Here, we're going to look at multiplying and dividing rational expressions. Here we have the product of two rational expressions. What we're doing here is we're multiplying the numerators and the denominators. So we have 3 times x squared times 4 times y cubed in the numerator, and the denominator we have 2 times y times 3 times x. Because the numerator is all multiplication and the denominator is all multiplication, we can cancel out like facts. Let's start with the 3. There's a 3 in the numerator and a 3 in the denominator. They cancel out. In the denominator there's a 2, and in the numerator there's a 2 times 2 for the 4. So let's cancel out one of those 2's, leaving a 2. In the denominator there's an x down here, and this x cancels out one of the x's in the numerator, leaving an x to the first. In the denominator there's also a y. This y cancels out one of the y's in the denominator, leaving a y squared. Let's work out our answer. What we have left then is an x to the first, so we write that just as x. We also have a 2, and I can put that 2 right in front of the x as a coefficient. And then we have a y squared. So we end up in the numerator 2xy squared. In the denominator, we can see that everything has been canceled out. So in our denominator, we have a 1. When there's a 1 in the denominator, we actually don't need to write it. So our answer is 2xy squared. This is our final answer, so we'll put a box around it. Here's another product of two rational expressions. Notice the negative sign out front. I can immediately move that negative sign out front into my answer. Do we have anything that cancels out? Let's see. We have a y squared in the numerator and a y squared in the denominator. They cancel out. We have an x squared in the numerator that cancels out with 2 of the x's in the denominator. So nothing else cancels out. So let's multiply across. 5 times 3 is 15 in our numerator. In the denominator, we have a 2, an x, and a 7. 2 times 7 is 14 times x. So this is a valid answer, but I wanted to show you there's actually more than one way to write the answer. I can have the negative sign out front. I can have the negative sign in the numerator, negative 15 over 4x. Or I can move the negative sign down to the denominator and have 15 over a negative 14x. All three of these are valid answers. The negative sign can be out front, it can be in the numerator, or in the denominator. We'll box one of these answers. They're all valid. In our first problem, we have to look for restrictions, and we have a 2y in the denominator and a 3x. So we know that y cannot equal 0, and also x cannot equal 0. If x or y are ever 0, we would have 2 times y, which is 0, or 3 times x, which is 0, which would make our denominator 0. We check for restrictions prior to our simplification. In our bottom problem, we have the same situation. If x is 0 or y is 0, our denominator will be 0, which is a divide by 0, which is not legal. So we also have to say that y will never equal 0 and x will never equal 0. Again, we check for restrictions prior to our simplification. And even in the simplified version, you can see that x cannot equal 0. Here's another example. We're multiplying two rational expressions. Let me put a parenthesis around this. So if you think about this, in the numerator, we are multiplying a binomial that's squared times a monomial. We'll put a parenthesis around our monomial. And in the denominator, we're multiplying a monomial, we'll put a parenthesis around that, times a binomial. So we want to, if we think about this as strictly multiplication, we have to hold our binomials together as one complete fact. Okay, I've moved this up. Let's factor the numerator. The numerator factors into x plus 2 times x plus 2 because the x plus 2 is squared. And we also have a 3x. So that's our numerator. Now let's factor the denominator. Well, we have a 6x squared, and I'm going to factor that 6 into a 3 times 2, and then I have an x squared. I'm going to factor that into an x times an x because I see an x above. And now let's factor this. This is the difference of two perfect squares, x squared and 2 squared. And as we know, the difference of two squares factors into two conjugate binomials. That is, two binomials such that the first term is the square root of the first, the last term is the square root of the last term of the original, and the signs are different. One is addition and one is subtraction. So these two binomials are considered conjugate. Their terms are the same, but one is addition and the other is subtraction. And when you multiply two conjugate binomials, you get the difference of the two perfect squares, the first term squared minus the second term squared. Let's continue our line here. Okay, now that I've factored this out, I can do some canceling. This 3 cancels out with a 3 in the numerator because it's strictly multiplication. Now I want to point out that the only canceling we can do here is to cancel out facts that exist both in the numerator and in the denominator. One common mistake I see is that some students will cancel out, let's say, this x here with this x here. These two x's cannot be canceled out because this x is a term, x plus 2, we add terms, within a fact. So this entire binomial is considered a fact. Its entire entity stays together. You don't want to pull it apart because it is a full fact. Now, what we can cancel out, though, is we can cancel out this x here with this x right here. And we can cancel out this x plus 2 with this x plus 2. In the numerator, all that I have left is a binomial fact, x plus 2. There are no binomial facts, x plus 2, in the denominator. So let's rewrite this. In the numerator, we have x plus 2. And then in the denominator, what we have left is we have a 2 times x minus 2. So a 2 times x times the binomial x minus 2. Okay, so we've finished up here. This is our final answer, and if you wanted, some students like to multiply this back. You don't have to, but if you did, in the numerator we'd have x plus 2, and in the denominator we would distribute that 2x back in and get 2x squared minus 4x. Both of these answers are valid answers. They have the same value, so I'll put a box around both of them. neither is superior to the other. They're both just fine. The reason that we factor, the difference here is the top one, the bottom is factored, and the bottom we've distributed it and put it in terms of terms. So in the bottom denominator, we have two terms, and in the top denominator, we have two facts, a monomial and a binomial. Both are valid answers. Let's look at domain restrictions, and to do that, we want to go up to the original problem. Okay, so 6x squared cannot equal 0. So we would say that x, and actually let's do our domain restrictions. Let's write them in blue. X cannot equal 0 because if x is equal to 0, 6 times 0 squared is 0, and we have a divide by 0 error. And the other restriction is right here. X squared minus 4 cannot equal 0. So what does that mean? That means that, let me get my pen out, if x squared minus 4 cannot equal 0, then if we factor x squared minus 4, we have x plus 2 times x minus 2 cannot equal 0. And that occurs when either x plus 2 equals 0, and that can't be true, or x minus 2 equals 0, and of course that cannot be a truth. So in our first expression here, x plus 2 equals 0, we add a negative x to both sides, and our restriction is x is not equal to negative 2. And in our second expression right here, we're going to add 2 to both sides and say x is not equal to 2 either. So our restrictions are that x cannot equal 0, x cannot equal negative 2, and x cannot equal positive 2. Another way to write this is to say that x cannot equal 0 or plus or minus 2. This is set notation. And let's put a box around that. So these are our answers. Here's another problem. We're multiplying two rational expressions. Let's change it up a little bit by getting rid of the subtraction. So this is add the opposite. This is add the opposite. And if we think of this as all facts, this is a binomial fact. This is a monomial fact. They are being multiplied. This is a monomial fact, and this is a binomial fact. They're also being multiplied. So let's move this up, and let's rewrite this. So I have in the numerator an x plus a negative 4, and that's being multiplied by a 10x. And in the denominator, I have a 5x. And when I look at this next binomial right here, 4 plus a negative x, let's swap this around. And we can commute because it's all addition now and say negative x plus 4. Okay. I'm noticing, though, that I have two binomials that look fairly similar, x plus a negative 4 and a negative x plus 4, but the signs are different. So I can fix that up. Before I do, let's cancel out the x facts, and let's cancel out the 5 from the 10, giving us a 2. And I'm going to rewrite the numerator as 2 times x plus a negative 4. And in the denominator, I just have that binomial left. But let's factor out a negative 1. If I factor out a negative 1, I get x plus a negative 4. And that matches my binomial in the numerator, which means these two binomials cancel out. So my answer is 2 over a negative 1, which can also be written as a negative 2 over 1, or more simply, and probably the best way to write it, is negative 2. So let's box our answer. And there are also domain restrictions. The domain restrictions occur when 5x is 0 or 4 plus a negative x is 0. So our domain restrictions occur when x, and we'll write this in set notation, is either equal to 0, because if x is equal to 0, 5 times 0 is 0, or when x is equal to 4, because 4 plus a negative 4 is 0. So let's include a 4 here. So there are two restrictions. X is not equal to 0 or 4. Here we have the product of two rational expressions. Notice that the numerator and denominator of both expressions are quadratic trinomials. So we're going to need to factor these. Let's move this up. Okay, we'll make this one complete fraction. It's multiplication all the way across. And our first quadratic trinomial will factor, and what we need to use to factor this is a split the middle term, right? Where we have what two numbers, m plus n equal 5, and m times n is equal to 2 times a negative 12. So when we factor this, we find that this factors into 2x minus 3 times x plus 4. Okay, let's factor the denominator. The denominator also has a lead coefficient that's not equal to 1, so this is going to factor using split the middle term. That's factor by splitting the middle term and then factor by grouping. And when we do this, we will get a 2x minus 3 times a 3x minus 1. Okay, let's go back up to the numerator here and get the factor of this quadratic trinomial. When we do, we will get a 3x minus 1 times an x plus 1. And now let's factor the quadratic trinomial in the denominator of the second rational expression. And this one is x plus 1 times x plus 4. This is probably the easiest one to factor because the lead coefficient is 1. And so we just need to find two numbers, 1 and 4, whose sum is 5, whose product is 4. Okay, let's look at what cancels out. We have a 2x minus 3 in the numerator and denominator, so that cancels out. We have a 3x minus 1 in the denominator and also in the numerator. We have an x plus 4 in the denominator, also in the numerator, and an x plus 1 in the denominator, also in the numerator. What's this equal to? Well, this is actually equal to, there's actually a virtual 1 always multiplied by every fact, so this is equal to 1 over 1. Therefore, our answer is simply 1. Now we also have domain restrictions, and to see the domain restrictions, we have to look at the original denominators, which are here and here, and if we factor them, we can see they factor into these four binomials. So the following is true. In our first binomial, we have 2x minus 3. Well, 2x minus 3 cannot equal 0. Otherwise, we'll have a divide by 0 error, which means that 2x cannot equal a positive 3, which means that x cannot equal a 3 over 2. Looking at our next binomial, 3x minus 1, well, 3x minus 1 cannot equal 0, which means that 3x cannot equal 1, which means that x cannot equal 1/3. Okay, there are two more. We have x plus 1 and x plus 4. Both x plus 1 and x plus 4 cannot equal 0. Solving for what x cannot equal, we have x cannot equal a negative 1, and x cannot equal a negative 4. So x can equal all values except for a -1, a -4, 3 over 2, or 1/3. So we would write this as x cannot equal, and we're going to write it in set notation. And usually when you write in set notation, you're going to go in numerical order. So our smallest number is -4, and our next smallest number is -1, then 1/3, and then 3 over 2. And here we have our restrictions. When dividing two rational expressions, we change our division to multiplication by the reciprocal. So that would mean we would start still with the 8x cubed over z, but instead of dividing, we multiply by the reciprocal or multiplicative inverse of the original function. That means the denominator 3 goes in the numerator, and the 5z cubed that's originally in the numerator goes to the denominator. Now, looking at this expression, I can see nothing that will cancel out. So let's go ahead and multiply things together. Let's move this up, and our multiplication up. Okay. So 8 times 3 is 24 times x cubed. And in the denominator, we have a coefficient of 5, and z to the first times z to the cubed is z to the fourth. We add exponents. So there's our final expression. The key here is when dividing rational expressions, change the division to multiplication and rewrite the second rational expression as its reciprocal. Here we have another example of two rational expressions, but we're dividing instead of multiplication. So what we need to do is rewrite the first rational expression, which is x squared minus 9. This is a binomial, and notice it's a difference of two perfect squares. And in the denominator, I have the binomial, which is linear, x plus 4. I'm going to change the division to multiplication by the reciprocal of the second rational expression. So the x plus 4 goes in the numerator, and the x minus 3 goes in the denominator. And right away I see that the x plus 4's cancel out, because it's strictly multiplication now, and I can cancel out with multiplication. Now let's rewrite this. Well, I notice that x squared minus 9 is the difference of two perfect squares, and the difference of two perfect squares factors into the product of the two conjugate binomials, x plus 3 times x minus 3. That's my numerator. In the denominator, what I have left is x minus 3. Clearly, I can cancel out the two binomials x minus 3 that are in the numerator and the denominator. My final answer is x plus 3. This is the simplified solution to this division problem. Now, once we look at this, once we have this as all multiplication, we can look for possible divide by zero errors. They occur first whenever x plus 4 is equal to 0. So x plus 4 cannot equal to 0, or we can say x is not equal to a -4. They also occur when x minus 3 is equal to 0. So I would say that x minus 3 cannot equal 0, which means that x cannot equal 3. So our restrictions here in set notation are that x cannot equal -4 or 3.